Welcome back. In this video, we'll be looking at Theorem 1.4.2. It says that if S is linearly dependent, then there exists an element V in S so that the span of S is the same thing as the span of S without V. Right, so we want to say that if it's a linearly dependent set, some of its vectors are redundant, and you could remove at least one from the set of generators and still get the same span. All right, let's prove this. Since S is linearly dependent, there exists a V in S so that V can be written as a linear combination of other elements of S. So A1, AN in R, V1, Vn in S, but not V, so S minus V. Right, so again, let me just make sure this is clear. This is S minus V. So all the elements of S except for V. All right, but that means that V is in span of S minus V. So let's take that V and we'll prove that the two spans are the same. So claim span of S minus V. So this V is redundant. I can already build it in terms of the other vectors of S, so I don't need it. I will build it independently. I don't need it as a separate generator. All right, so this is what I want to prove. As usual, what I'll do is I'll show that each set is included in the other one. So first I want to show that span of S minus V is inside span of S. So for that, I'm going to look at, it's a bit of a way back, it's when we started comparing span. If S is in span, oh yeah, this part here, I'm sorry, it does not filled. I keep changing documents every section. So if S is inside span of T, span of S is inside span of T. That's what we'll use. All right, so let's go back to where we were here. So I have that S minus V. Well, it's everything in S except V, but it is in S, and S is in span of S. So because this subset is inside span of S, then the span of it will also be inside span of S. And this is a bit obvious intuitively. If I take fewer generators, I take the same set of generator, I remove a few and I build a span, I'm going to get something smaller or equal, but included in the original span. All right, second part, I want to look at span of S and show that that's inside span of S minus V. That one is less obvious, and for that one to be true, we needed to pick V carefully. All right, so since V is equal to A1 V1 plus AN Vn, it is in span of S minus V. All right, good. So we have that V is in span of S minus V, but of course S minus V is inside span of S minus V. So every element of S is in span of S minus V, either because it is in S minus V or because it is V and we've picked V that is a linear combination of the rest. All right, good. So then that means that the whole set Z is inside span of S minus V, and so that means span of S is inside span of S minus V. All right, so we proved one inclusion here, the other inclusion here, so the two sets contain each other, and that means that span of S equals span of S minus V. All right, so V was a redundant vector. I didn't need it to get everything I wanted. Not needed as a generator.